One way to define Lyapunov stability is using the direct method. This involves taking some function v of our x dot equals f of x system. We then look at some alpha 1 and 2 which have zero initial condition and are non-decreasing in x. If v of x is less than alpha 1 and v dot of x is less than alpha 2 for all times greater than t naught, then x is stable in the sense of Lyapunov. Next, we consider some system x dot equals a of x. We define p of x such that x transpose times p times x forms some ellipse around an equilibrium point with a length of 1. Taking a look at the graph, we see the tangent of the trajectory x of t is a of x, and the normal line to the outside of sigma is p of x. In order for stability to hold, we need p of x times a of x to be less than 0, which means that transpose a times p plus p times a is less than 0. Since p of x dot product with a of x dependent on the norm of p and the norm of a, we need cosine of theta to be negative. So that means our angle between ax and px must be between 90 and 270 degrees. This is true for all x. We can make our sigma field smaller and smaller and say the system is Lyapunov stable. We will now go into a broader discussion of what being stable or unstable means. There are generally three types of stability. The first category is Lyapunov stability, which means for some x starting within some range delta of an equilibrium point, it will stay within another range epsilon of this equilibrium point. This corresponds to real components of eigenvalues that are less than or equal to 0. A real-life example of this is shown here. We define our epsilon to be the dirt circle and delta to be the spinning wheel. Notice here this is a stable system. Right about now, the system becomes unstable. The next form of stability is asymptotic stability. This means that when we start within some range delta, our trajectory will head towards the equilibrium point as time goes towards infinity. A real-life example of this is shown here. Notice that wherever the trajectory starts, it always winds up at the same point. No matter how close we are to the top of the slide or delta, we will always wind up at the bottom. The last form of stability is global stability. This means that no matter where we define our delta, our trajectory will always head towards the equilibrium point. In our world, there's no such thing as absolute global stability, but there can be global stability depending on our frame of reference.
One last example is the orbit of the Earth. Have you ever wondered how the Earth always stays in the same orbit, never taking any more time to rotate around the Sun once? Since the pull of the Sun's gravity is stronger once we get closer to the Sun, you would think that if the Earth was slightly bumped towards the Sun, such as if you jumped or something, then the Sun's pull would get stronger, resulting in the Earth moving closer to the Sun, causing the pull to get even stronger and eventually causing the Earth to spiral into a fiery doom. But you, me, and ME 564 lectures are evidence that the Earth doesn't spiral into our doom. So how come? When the Earth gets pushed slightly towards the Sun's increased pull also speeds up the Earth. So even though the pull is now stronger, the Earth will have enough velocity that it will overshoot and ends up further away from the Sun. At this point, the Sun's pull will slow it down again, and the Earth will return to its original trajectory. The two effects of speeding up and additional gravity balances perfectly. So the Earth stays in the stable orbit just like a marble stays in the bottom of a bowl, even if you knock it around a bit. This demonstrates Lyapunov stability.